Welcome back. We've been talking about looking at math as a second language. If you look at math as a language, it may be effective in reducing some math anxiety. And that's been the subject of the past 3 tapes. We're talking with Herb Gross and Sandy Shugart. I'm Susan Brown. Herb, we've seen that math anxiety, as it's called, can be perhaps eliminated by making the language of math something that is comfortable for students. If we encourage them to become bilingual, that's a step towards succeeding in math. But at some point, we have to talk about formulas, definitions, and can we then take a look at reducing math anxiety? Does it rear its ugly head again when all of a sudden we have to memorize rules, and there are things now that cannot be simply explained in terms of fractions or whole numbers or reducing it to its lowest common denominator?
Sure. There's a lot of that. I'm also reminded of the story of the immigrant who sacrificed everything to send his son to college, and ultimately the young man graduated with a PhD in physics, and the old man said to him, "Now that I've mortgaged everything so you can become a PhD in physics, maybe you could make an old man happy. Tell me in layman's terms what Einstein's theory of relativity was all about." And the kid looked at him and says, "Dad, it's simple." He says, "If you're in the arms of a beautiful woman for an hour, it seems like a minute. But if you're sitting on a hot stove for a minute, it seems like an hour." And the old man looked at him and said, "For this, Einstein made a living." Okay, I mean, certain things can be oversimplified. One of the problems with this language approach is we have to remember that just because you understand the language doesn't mean it's not hard. See, I have this problem with a lot of students in science. They've been told, if you're not good at math, you're going to have trouble with physics and chemistry, etc. They get A's in math. And now they don't understand it because they're still having trouble with chemistry and physics. See, the idea is chemistry and physics are hard enough that even if you know the math, you may still have a problem. But without the math, there's no hope that you're going to be able to get through some of this stuff. I remember back in about the 6th grade or so, it's a riddle that still perplexes people. I thought it was just a kid's riddle. Do you remember this, when something like this? I'll write it down as we say it. Brothers and sisters have I none, but this man's father is my father's son. Now, is there any word in there that's hard to read, hard to understand?
No.
You know, what word gives you trouble? I think, but do you see the riddle effect here, the tongue twister? Brothers and sisters have I none, but this man's father is my father's son. And you try to analyze that. You see, what's interesting is, if you have no brothers and sisters, your father's son is me, or I guess. And now all this says is, this man's father is me. I am this man's father. You see the riddle here? See, brothers and sisters have I none, but this man's father is my father's son. That means that this man's father is me. That's all this says. But notice that there was no foreign language here. So going back to that Einstein story, if I didn't know German and somebody said, "Here's Einstein's theory of relativity," and I read it, oh, I would understand. I can't possibly understand this. It's written in German. That's true. Doesn't mean I would understand it if it was written in English. And you see, ultimately, the question of the real reason that we use mathematics is for critical thinking. For example, if you go up, there is one problem of the kid who doesn't know what 3 times 9 is. That problem can be solved with a hand calculator, for example. But the problem I see that's much bigger is this one. You go up to a little kid and you say, "How much is 3 times 9? He says 27. You say, "Great. Now at $3 each, how much will 9 ballpoint pens cost?" He says, "I don't do word problems." See, that's where the math illiteracy is coming in to hurt us the most.
Right.
And so rather than just talk about the language part, we have to talk about the mathematical structure after a while. And in terms of our analogy with language, what it says is, even after you know language, you have to understand something about the abstractness of language. See, that some people understand language, some people write better than others. Why isn't everybody an author? And you know, even in language, there are lots of rules that you take for granted. You see, why can't you end a sentence with a preposition? What are you, a barbarian if you do that? In fact, it's kind of, you know, it's interesting, you know, people forget that in the phrase Anglo-Saxon, the English part is Anglo, the German part is Saxon. And so we have a lot of German in our language, and German has separable prefixes. You know the old story about Churchill saying, correcting my grammar is something up with which I shall not put.
Right.
I told Susan
Right.
a story before that she liked about the little boy who was sick in bed. He was up in his bedroom on the second floor, and he wanted his mother to bring up a book, and she brought the one book he didn't want. And he looked at her and gave her a sentence that ended in 5 prepositions. He said, "Mother, why did you bring the book from which I did not want to be read to, out of, up for?" And it starts with from which.
Yeah.
You see, so what occurred to me, and you may recall that last year we did a series called The Teacher as Coach. I happen to like sports a lot. And basically, there's something about the structure of a game that not only categorizes all games, but it's also a good way to look at the learning process. See, the way this came up in my life was people would say to me, I was great in math until it became too logical. Other guys said, I could handle the logic, but it was just too much to memorize. And I say, what part is logic and what part is memory? And the interesting thing is, when you think of what a game is, see, what is a game? See, what is it that all games have in common? Well, for example, the objective of every game is to win. So to say there's an objective, that doesn't say much. It just says to win. Somebody says to me, well, how do you win a checkers game? I say, well, you have to capture all of your opponent's pieces. So I'm playing checkers with Sandy. I say, hey, Sandy, look up there. While he looks, I grab all of the pieces. See, now I've captured all of the pieces, but I don't win. Why? Because there's no rule of the game that allows me to do that. If there was a rule that says if you're dumb enough to look up and your opponent takes all of your pieces, you lose, then you deserve to lose.
Right.
See, it's not just winning, it's winning according to the rules of the game. But what are the rules of the game? It comes back to language again. If I don't know what a strike is, I don't know what an out is, what good is it for me to be told that 3 strikes is an out? You see? Basically, see, so let's look at that. Let's look at the structure of a game. You see, on the ground floor, you're going to have definitions. I'll just write DEF. This looks very nice for everybody. Then after you have the definitions, you have the rules. See, the rules are the relationships between the terms. Then you have an objective, which is usually to win. Okay? Now, the reason I like this setup is, how do you learn the definitions and the rules? You memorize them.
Right.
See? Now, you can make the definitions more palatable to somebody. For example, somebody says to me, how come there's 52 cards in the deck? I say, well, it's simple. There's 52 weeks in a year. 4 seasons, 13 weeks each. That's great. Does that mean, though, that to a guy who plays pinochle, where there's 48 cards in the deck, there's only 48 weeks in a year? See, you can give mnemonic devices to remember things. Or a guy says, how come there's 3 strikes is an out in baseball? You say, well, anybody knows that. 2 wouldn't have been enough, and 4 would have been too many. No, are you allowed to memorize that 3 strikes is an out in baseball? Sure. Not only are you allowed to, there's probably no other way of learning it. So in other words, the definitions and the rules, I guess we can call rote. We just memorize them. But how do you gain the winning objective? You apply the definitions and rules by something called strategy to arrive at a winning situation. Okay? So in other words, now using hindsight, a game is any system consisting of definitions, rules, and objective, where the objective is carried out as an inescapable consequence of the rules and the definitions by strategy. And the strategy is the logic part. See, most people are used to, for example, we don't call football and baseball contradictions because they're not the same game. They're played with different sets of rules. See, what would be a contradiction is if you had contradictory rules in the sport. For example, if 3 strikes was an out, was a rule, and also 4 strikes was an out, was a rule,
Right.
the first time there was 3 strikes, the game would be over. Because both sides would be able to quote a justifiable rule. See, and in the game of mathematics, after a certain amount of intuition, it comes down to the stage where either something can be demonstrated or it can't be. See, let me see if I can give you a few examples. A lot of people get, let me just write down, you mentioned the word formula, right? Let me just write down the formula for the heck of it. Hope this scares everybody. This is one time when I want people to be scared if you have math anxiety, because my golly, that doesn't look like a very easy thing to read. By the way, for those who are initiated, this happens to be the formula for converting Fahrenheit to Celsius. And hopefully we'll come back to this before this part is over. But the idea is this. First thing you see over here is parentheses. Well, mathematicians use parentheses for the same reason that in English grammar we use hyphens. For example, I'm going to just leave this over here so I'll make sure I still have it. I'll come back. I want to remember to come back to that. See, if I wrote down this phrase, the high school, I don't have enough room on one line, but it's too bad. Doesn't matter. The high school building. And I don't pronounce it. Can you see two completely different meanings?
Right.
Is it the high school building,
Or the high
or is
school
it the high school building?
Right.
And if we mean the high school building, we usually put a hyphen here and make this into one word. It's like that weekly, you know that weekly reader little joke where the one kid says to the other kids, have you ever seen a man-eating shark? He says, no, but once in the restaurant I saw a man eating tuna. See, I mean, the change of the phraseology.
Sure.
See, in math we don't use the hyphen, we use parentheses. See, everything inside parentheses is treated as one number. And the reason for that is to avoid certain ambiguities. In the same way that the high school building can have two meanings. And by the way, if you want a complete sentence this way, it's they don't know how good meat tastes. This is a great example to show you what happened in the English language because we were sloppy with our rules. If you look at the sentence, they don't know how good meat tastes, it's impossible to tell whether good is an adjective modifying meat or an adverb modifying taste. In other words, are these people who have only eaten bad meat, so they don't know how good meat tastes, or are they people who have never eaten meat at all and they don't know how good meat tastes?
Right.
See, voice inflection again. Well, see, look what happens over here. If I say to you, how much is 9 plus 3 plus 1? Okay, one person might say 9 plus 3 is 12, plus 1 is 13. In other words, you read it as if it was grouped like this. Another person says, maybe he meant 9 plus 3 plus 1. See, maybe he meant this.
Which makes no difference in addition.
Makes no difference at all in addition. Okay. By the way, you know what the difference is? It's whether this grouping implies you're adding from left to right. This grouping implies that you're adding from right to left. See, the 1 plus the 3 is 4, and the 4 plus the 9 is 13. By the way, notice that when I read this from right to left, I'm saying 1 plus 3. Is that the same as 3 plus 1? Does order make a difference?
Not in this.
Not in this, but in real life, does it? Does it make a difference whether first you undress and then you shower, or whether first you shower and then you undress? And I'm not
that
taking
makes a
sides. I'm just saying whichever way you do it. Do you remember the other way is different?
Yeah.
See, in other words, in general, order does make a difference. I'm going to come back to this in a minute, but I want to show you why. Remember in our first program we talked about the kid saying 89 plus 4? The kid hears that first number, he hears 89. Then he says plus 4, 90, 91, 92, 93. He tended to hear the problem in the order that the numbers were read.
Right.
Say to that same kid, this is a nice experiment you can try with child behavior, growth and development, whatever you want to call it. Say to that same kid, how much is 4 plus 89?
5,
6, 7, 8, 9. He says,
10.
wow, this is a hard problem.
Yeah, it is.
It's not intuitive that 4 plus 89 is the same as 89 plus 4. And to say that it is causes a heck of a problem. See, here's what the failure of the new math was, in my opinion. In the old math, we said 3 plus 2 was 2 plus 3 because all you did was change the order. In the new math, we said 3 plus 2 equals 2 plus 3 because addition is commutative. Now you say, what does commutative mean? It says, oh, you can change the order. See, nobody ever pointed out that, hey, it may be an advantage sometimes to know that you can change the order in addition. You see, you can't do it in subtraction. Well, let me modify that. You can do it in subtraction, but you get the wrong answer. See, suppose I take a problem like 9 minus 3 minus 1, and I read this from left to right. See, 9 minus 3 is 6. 6 minus 1 is 5. So reading it this way, I get 5. Now let's read it this way. 1 from 3 is 2. 2 from 9 is 7. See, if I group it like this, Susan, you see what I'm saying here? 9 minus 3, that's one number, that's 6. And 6 minus 1 is 5. If I group it this way, 3 minus 1 is 2.
Right.
See, it makes a difference, doesn't
Yeah,
it?
it does make a difference.
Now, by the way, watch how this helps your number sense. See, suppose I were to write down, see, when you learn that you can group and rewrite any way you want in mathematics, suppose I say to a kid, how much is 3 plus 4 plus 5 plus 7 plus 6 plus 5 plus 2? A lot of work here, right? But I can build tens. I know it's what? 3 plus 7 is 10. 4 plus 6 is 10. 5 plus 5 is 10. There's 3 10s right there. There's 30, and 2 more is 32. See, I give a kid a problem like 4 times 76 times 25. If I know that it's safe to change the order, isn't 4 times 25 easy to do? 4 times 25 is 100. And how do you multiply by 100? Tack on 2 zeros. See the adjective and noun again? You want the 76 to modify hundreds, so you have to show that there are no 10s and no 1s. You have 76, hundreds over here. So you say 4 times 25 is 100. 100 times 76 is 7,600. And look how easy this problem has become. And even if you're using a calculator, you now have a number sense as to what's going on this way. See, logic is a very, very important thing. Sometimes by knowing what can't work, you can always find out what does work. I don't make up many riddles, but one of my favorite is, I'll probably draw this badly. You have a 6x6 checkerboard. Well, I'll draw this awful, but that's okay. We're going to test the acumen of the control booth now. Have a 6x6 checkerboard. That gives me what, 36 squares? Okay, I've got 12 checkers. I'm going to put 1 checker in each corner. And now the object is to put the remaining 8 checkers down so that no row, column, or diagonal has more than 2 checkers on it. Well, I'll give you the answer. An answer. One answer is this. But what's really neat about this is figure out where they can't go. There's already 2 on this row, isn't there? So we can't put any over here. There's already 2 down here. Can't put any over here. There's already 2 over here. Can't put any more there. There's already 2 over here. Can't put any more over there. There's already 2 down this diagonal. Can't put any more over here. There's already 2 on this diagonal. Can't put any more over here.
So there you go, what's left
There you
over.
go, what's left. See, it's a real neat thing. And what allows us to do that? Logic, strategy. Let me show you an example that I use very effectively, I think, to teach inmates. Outmates works that way too, okay? Let me just do an example kind of quickly over here. I say to an inmate, how much is 1/2 plus 1/3? They don't want to say 5. They don't want to find common denominators and stuff. They say it's 2/5. They add the 2 top numbers, add the 2 bottom numbers. Let's go back to the logic and adjectives and nouns again. I say to them, you work 30 minutes one day and 20 minutes the next day. How many minutes do you expect to get paid for?
50
50.
minutes. That's a
But
whole number
sure,
problem.
whole
Easy.
number problem. But watch the logic now. Isn't 30 minutes another name for 1/2 hour?
Right.
And isn't 20 minutes a name for 1/3 of an hour, because 60 minutes divided by 3 is 20? And what did they just tell me? 1/2 plus 1/3 is 2/5. 2 out of 5 is the same as what rate out of 60? 2 out of every 5 minutes, 5 goes into 60, 24. Now I say you can only get paid for 24 minutes. See, I've applied strategy to their rules, and I wind up with an objective that they don't want to live by.
Right, they don't like that.
They don't like that. I didn't tell him to change. If that poor guy serves 30 years, when he gets out, they said, what'd you learn in jail? He said, I learned that 1/2 plus 1/3 wasn't 2/5. You see what I'm saying this way? See,
Sure.
now the same thing happens with formulas. See, let's go back and see what this means again. And, I think this will finish my share for today and just see if you get the idea of this. See, F stands for Fahrenheit. And what does this mean? You start with the Fahrenheit and subtract 32. How do I know I subtract 32 first? Because it's in parentheses. Everything inside parentheses is like a hyphen. The 5/9 over here, there's no time sign. See, when you use formulas, you don't use a time sign because the time sign looks like an X. So you just put the multiplier next to this thing. What does 5/9 mean? It means 5 out of every 9. You're going to divide by 9 and multiply by 5. This looks hard, doesn't it? Watch what this says, though, when you translate it into plain English. In fact, I'll put this aside now, and we'll just translate it. The F means you start with the Fahrenheit. I'll just write out F-A-H-R for Fahrenheit. Next statement said what?
Subtract 32.
Subtract 32. Now, to multiply by 5/9 means you divided by 9 and you multiplied by 5. And the answer is Celsius. So if I said to you, convert 68 degrees Fahrenheit to Celsius, you put the 68 in here. Now you're going to subtract 32. With or without a calculator, that's going to come out to be 36. Now you're going to divide by 9 4, that's 4. Multiplied by 5,
20.
that's 20. So 68 degrees Fahrenheit is 20 degrees Celsius. That's all this formula here says.
And that's a basic game strategy
Basic
to
game
break down
strategy.
a complicated
Yes,
problem into a
yes,
series.
and in fact, from another point of view, the difference between algebra is the other side of arithmetic. Arithmetic is when you see, what you see is what you get. Algebra is when what you see isn't what you get, and let me explain that. If I read this from top to bottom, see, the thing of this is a computer, input and output. If I read this from top to bottom, when this says subtract 32, I subtract 32, don't I? Watch what happens if I tried to reverse this. Suppose I knew that the Celsius was 20. When did I get to 20? After I multiplied by 5.
Right.
See, this says what? Blank times 5 equals 20.
Right.
So even though this says multiply, when I reverse the steps, this is going to say what? Divide by 5.
Okay.
Well, if I divide 25 by 5, that gives me the 4. When did I get the 4? After I divided by 9. So now I want to undivide, which means multiply.
Right.
4 times 9 is 36. When did I get to 36? After I subtracted the 32. So now I want to unsubtract. 36 plus 32
And you'll
is
get your 68 degrees.
Okay? But now, if I take this formula, and if we can take a look at that, I just wanted to see what the difficulty is. When we take this formula and we say multiply both sides by 9/5 to get rid of this, you see people with math anxiety going crazy over this? But all we really did was to say, look at, if first we divided by 9 and then multiplied by 5, when we reverse the steps, we're going to do what? Divide by 5 and multiply by 9. And now do you see even algebra being taught as a second language?
Yeah.
You see what I'm saying?
They're the same principles that you
Same
apply to
principles.
arithmetic. If
Same
you know
principles.
arithmetic, you know algebra as well, if you approach
Yes.
it as a series
Yes.
of arithmetic problems.
And there is one big difference, though, between the, there is one big difference between the game. See, mathematics is a game, too. Most people don't realize that. English is a game. For example, if a kid says, you know, why can't I use double negation? Or why can't I split an infinitive? We don't have to say because you're a barbarian. You say, look, that rule is no more logical to me than the rule in baseball that says 3 strikes is an out. But if you want to play the game of good grammar, these are the rules that we accept. Now, are we making the kid memorize? Yes, but we're also letting him see that it's not that self-evident. Can you visualize 2 guys trying to learn chess, and one guy, the first guy has a hard time memorizing the moves, second guy has an easy time? Can you visualize that a year later, the guy who had a hard time memorizing how the pieces works is still a great player, and the other guy is still memorizing strategies? In other words, how long it takes you to become comfortable with the definitions and the rules has no bearing on how well you're going to play the game later.
Yeah.
But too often, we make the definitions and the rules so important that the student drops out before he even realizes that that's the important thing.
Yeah.
You see what I'm
He
saying?
never
that
plays
way?
the game.
Never plays the game. See, the same in mathematics. See, a kid says to me, I don't believe that this is not self-evident to me. So I say to the kid, it better be self-evident by Friday because we're going to have a test on it. And God help you if it's not self-evident. But suppose the kid says to me, this isn't self-evident. And I say, look, it's not self-evident to me either. It's a rule of the game, just like 3 strikes is an out in baseball. And you see,
But at this point, though, that they understand the language of
Sure.
math much better,
Yes.
so that they are not only willing to take a chance at trying to learn this math, but they've already had some successes, so that they are more able to take a look at it and
Sure.
be successful.
and by the way, even if a kid understands baseball, is it possible he won't like to play it?
Sure.
Sure.
Yeah.
Sure.
And by the way, if you think there are too many kids playing Little League now, you want to get rid of kids playing Little League? Tell them that before they can play baseball, they have to get the official Major League rule book and memorize all the rules before they can play. What's going to happen? They'll have how do you teach a kid to play the game? Don't you take them out there, and as soon as something happens, you stop and explain why this was done, and they learn from the context?
That's
Right.
right.
Let's teach
That's
to play
right.
math that way. You see, the difference between math and baseball is that in the game of math, the objective is to explain the real world. And therefore, the reason that we want our rules to be self-evident is because of the logical idea that if the rules don't make sense, how can the strategies that you derive, or the results that you derive from using the rules make sense? In other words, if the rules are unrealistic, the results will be unrealistic. See, we don't use the word rules of the game in math. We usually call them axioms and postulates. And all an axiom is a rule of the game. And we make it self-evident because we want the game to be self-evident. The only difference between a pure mathematician, I don't mean in moral thing, but what we call pure math and applied math, is that the applied mathematician plays with rules that are based on how we perceive the real world. The pure math simply picks rules that are logically consistent. And if someday those rules happen to fit some real life thing, we just take that whole body of knowledge and apply it to that particular life skill. And I think that's basically what we've been talking about. I don't know how you feel about that, Sandy, but you see there is a language involved, but after the language you still have to have reading comprehension. We're not all equal as players, and so we're not all going to be equal as mathematicians.
Right. And we don't talk about people having baseball anxiety.
That's right.
Or maybe even French anxiety. And
Sure.
yet the problems that you're talking about are similar to problems in learning any of those
I
things.
think so.
Okay. Well, that brings us to the conclusion, really, of our four-part discussion about math anxiety with Herb Gross, Susan Brown, and myself, Sandy Sugart. We've covered some ground, not with the intention really of teaching much math, but the idea of illuminating what math anxiety might or might not be about. And maybe the important point is that it's all tied up in language. If you can learn to translate math into your language and ultimately learn to understand the language of math, you don't have math anxiety problems at all, and maybe then the math can be mastered. Thank you for joining us in these discussions.